Okay, so the second video on climate is about PINDIC. Climate change policy, what do the models tell us? And if we go straight to its abstract, very little. Okay, and in fact he says at the end of his abstract, IAM-based analyses create a perception of knowledge and precision. We think we know something, but that perception is illusory and misleading. So they can be worse than useless, because we think, okay, now we know that the social cost of carbon is $80 a ton, and therefore we should have policy to achieve that as well as we possibly can, and then we find, of course, it might be 90, it might be 70, but we've got a pretty good idea. Whereas PINDIC is saying, look, these models, they might give us some kind of lower bound, but it could be 1,000. Okay. That's kind of what he's saying. And what does he base that claim on? We're going to jump ahead. So let's have a quick look before we jump ahead to what he bases the claim on. How does he characterize what these IAMs are? And we should be able to recognize this from Golosov et al. That we just looked at, right? 6 elements. 1, projections of future emissions under business as usual and one or more abatement scenarios. So we need a model of GDP growth, the energy sector, etc. to work out like what's going to happen without a tax, what's going to happen if we put the tax in. That's exactly what we got out of Golosov, right? Then we need a model of the atmospheric stock of carbon. We also saw that in Golosov. Then we need a model of how temperature is affected by the atmospheric stock, and then how the stock affects temperature, and then how temperature affects the economy. And Golosov wove those two into one step, based on arguments, basically saying, look, when we put together what Nordhaus did into one step, it just turns out really simple, so we're just going to do it like that from the start. Then we need to know how much it's going to cost to abate emissions. And of course in Golosov, that's really nice because they have this explicit model with inputs of coal, oil and renewables, and then they can say, like, the cost of abatement is what it costs to switch from coal to oil, which reduces emissions, and even better, from oil to renewables. So that kind of drops out of their model really nicely in the kind of way I've argued for earlier in the course, that you have explicit model with inputs making product and then leading to polluting emissions as a byproduct. You've got a really solid base. And then we need assumptions about the utility function and the time preference. And remember, Golosov, they had this log function. Utility at time t is the log of c. Okay. So what's the big problem according to PINDIC? Well, he mentions 2 or 3 things. It's a pretty focused paper, this, actually. So one of them is climate sensitivity. Climate sensitivity is defined as the temperature increase that would eventually result from an anthropomorphic doubling of the atmospheric CO2 equivalent concentration. CO2e, this is equivalent, so it's not just carbon dioxide, it's methane and nitrous oxide and so on. 2. But we really just don't know what's going to happen, and this is a sort of natural science problem, because there's so many feedback loops that, according to PINDIC, we won't know until we actually do it. Okay, this is basically his argument. because to really find out we need to perform experiments, but we don't have sort of multiple globes to perform experiments on. We can kind of perform small scale experiments and test ideas and so on, but it's open to debate how well we can really identify this relationship. And Pindyck is at one end of that debate and saying, look, we're always going to be very uncertain. Let me just pause. Okay, and then Pindyck's second point is that we just don't know the damage function. So if temperature goes up, how much is that going to affect GDP? Again, we just don't know. We can make educated guesses, we can look at rainfall patterns and measure what's going to happen in agriculture, etc., etc. But according to Pindyck, the uncertainties about what will actually happen in the economy when these temperature changes kick off, well, of course, they're already kicking off. We just don't know. And even up to now, we don't know what the damages have been, because we don't have a parallel Earth without the damages to compare with, to say, okay, on our parallel Earth they had this GDP, and on our Earth we had the other GDP. Okay. Then he also has a really odd argument about growth on page 867, 868, which to me does not make any sense, and I'm a growth guy. Okay. Then his sort of killer blow is catastrophic outcomes. Because he's basically saying, look, so the most likely outcome is a modest temperature rise. Maybe we can have a vague idea about what the damages are going to be. But what if there's a really whacking great temperature rise? And then it's like, okay, are the glaciers really going to melt, or the ice shelf going to collapse? Will sea level rise by 1 meter, or by 10 meters, or 15 meters, or whatever? Is this going to kick off massive wars, or, we just don't know. And the point is that if these outcomes are unlikely enough, then we can kind of ignore them. So like, if you've got a nice normal distribution, then these extreme outcomes, the probability of them goes towards zero very quickly. So they don't weigh heavily in the overall scheme of things. But of course, the probability distribution for outcomes of climate change is definitely not normally distributed, because we're definitely not expecting like positive benefits. If we had normal distribution, if this is no damage, so this is like damage here, and this is the probability here, so we've got some kind of probability density function, we're certainly not expecting any chance of negative damages, in other words, positive benefits. So clearly the distribution is going to be something like this, right? So then the question is like, how quickly does the probability approach zero here? Does it approach quick enough that these very bad outcomes don't really have any weight, and the key thing is the most likely outcomes? Okay. And it's not at all clear that they do approach zero quick enough. Okay. It could be that the probability density function is fat-tailed. Okay, it has a fat tail. If it does, then we really need to worry about the catastrophic outcomes, and those will basically be determining the social cost of carbon, not this outcome. And the social cost will be a lot higher. And this point was made in literature, which is cited by Pindyck, like if we go to the end, like Weizmann, 2009, for instance. There's a paper from even earlier, 2007. I can't remember. I'm not sure if it's in this list. I can't remember the author. It's probably there. Okay, I'm going to take you through a little bit of math on this fat-tailed stuff, okay? And I just want to pause to get myself ready for that. Okay, so fat-tailed distributions. So I'm going to start by giving you an example of a distribution that doesn't have a fat tail. Okay. And that distribution is just P equals e to the minus d. And we can do a quick check that this is an okay distribution, and we want to let d vary from 0 to infinity. Okay, so it's unbounded above, but it can't be below 0. So what's the integral of p dd between 0 and infinity? It should be 1, because something has to happen, yeah? So when you integrate the PDF over the range, you should get 1. So the integral of e to the minus d is just minus e to the minus d. Differentiate that, you get e to the minus d, don't you? Between the limits is put infinity in here, e to the minus infinity is 0, put 0 in here, that's e to the 0 is 1. When you put this one in, you take it minus, plus this one, minus that one, so we've got minus minus 1 is 1. Okay. So I'm happy with my PDF here, and it looks like this, yeah? So the most likely outcome is no damages according to this simple PDF, and then the likelihood of different levels of damages goes down as the damage goes up. What's expected damage, E of d, is the integral over the relevant range of d of d e to the minus d. So it's the damage level times its probability, yeah? It's d, pd, yeah? The integral of p times d. dd. Okay? So it's the sum of each probability times the damage of the associated probabilities. If this was discrete, this would be totally simple, wouldn't it? You would all see that straight away. With continuous values of d, it's the same idea. Sum up damages times the probability of each damage level. This integral is probably trickier than any integral you've ever done, but it's as integrals go, it's extremely simple. The answer is minus 1 plus d e to the minus d. If we differentiate that back, we have minus e to the minus d. Differentiated is e to the minus d. And then we have minus d e to the minus d. Differentiate the d, we get minus e to the minus d. So those two go out. And then we have minus d e to the minus d. Differentiate this part, and we have plus d e to the minus d. So that's the integral. Evaluate between 0 and infinity, and what do we get? We put in infinity here and we get nothing, so that drops away. We put 0 in here and switch the minus to a plus, and we get 1 plus d, which is 0, so that's 1. So expected damages are just 1, given this function. So this is not fat-tailed, okay? It's not fat-tailed because expected damages are like here somewhere. There's nothing, this lot isn't weighing heavily. But now I'm going to show you a function that is fat-tailed. Okay, what about a fat-tailed distribution? Well, this isn't my expert area, but it seems to me this distribution would be fat-tailed. Let's assume that P is equal to 1 over 2d squared. I've got a crib sheet over there, I don't know if you can see it on camera. Then to check that this is we're going to let d vary from 1 and up. So when d is 1, p is a half, isn't it? And then as d goes up, this is going to go down to 0. Clearly it approaches 0 as d gets big. But what's the expected value of d? First, let's check this is not a good PDF. So let's integrate p between 1 and infinity dd. So the integral of this, d to the minus 2 integrated, I don't know where this 2 came from, that's total rubbish, isn't it? It should be just 1 there. Got that wrong. D to the minus 2 integrated is minus d to the minus 1, isn't it? Differentiate this and you've got minus d to the minus 2. Sorry, minus minus. So you've got plus d to the minus 2. Okay, and put the limits in. That goes to 0, put 0 in. D to the naught is 1, and then this is negative, minus minus is plus 1. Okay, so this is a nice PDF as long as we let d go from 1 to infinity. So now let's look at e of d. But now we're not going to let d run to infinity because I already know we're going to crash if we do that. So we're going to let d run from 1 to something arbitrary, we'll call it a. And then we're integrating pd dt. Okay, p is 1 over d squared, so pd is 1 over d, or d to the minus 1. dd. Okay, integrate d to the minus 1, what do we get? That's log d, isn't it? Differentiate log d, what do you get? You get d to the minus 1. Evaluate log d at the limits, what do you get? Log of infinity, sorry, at the limits a and 1, log of 1 is naught, isn't it? Log of a is log a, so you get log a is the answer. So e of d is log a, so therefore e of d approaches infinity when a approaches infinity. So if the probability function looked like this, then things will be looking really, really horrible for climate change, right? Okay, so what does Pindyck conclude from this, section 4.2? He says, look, we should be like weighing up options in a much more, not pretending that we can do this with numbers, but just weighing up risks and options in a much more kind of, I don't know, intuitive kind of way, I suppose. Okay, I think that's what I wanted to say about Pindyck and probability functions and stuff. Okay, a few more words. I just saw this last bit on Pindyck, which was kind of interesting. He's saying, look, why don't we treat the IAM kind of numbers as a kind of minimum baseline, assuming based on this kind of part of the distribution, and say, well, let's at least take action based on that, but then let's work hard to weigh up. Should we be going a lot further due to what might happen out here? Okay, and at that point we're going to stop looking at the IAMs and look at what, just assuming some typical IAM level for carbon, the social cost of carbon, what would this actually lead to in the social planner's economy?